So let's finish up the processes. I think the only one I haven't covered is adiabatic. You mind closing the door? Oh, where's the example? Found a good example, but I cannot for the life of me. Let's see, adiabatic. Maybe toward the end. Oh my goodness, where is it? I was all ready for it. This is one very good example of an adiabatic system. It has a specific phrase in it. So, in real life, adiabatic systems, there's no true adiabatic systems. An adiabatic system is a system where no heat goes in and no heat goes out. Meaning the total heat is constant. However, we can get an approximate. If you have a piston or some system in which you compress the gas quick enough, you can compress it so that there's not enough time for the heat to escape. So during that one cycle, we can get an adiabatic process. Um, this isn't adiabatic, but I wanted to go over it anyway. I'll find the adiabatic later. So let's look at this example. An ideal monatomic gas is compressed from 12 liters to 3 liters at a constant pressure of 2.5 atmospheres. Heat is added to increase the pressure at a constant volume until the temperature reaches its original value. Calculate the total work done by the gas and the total heat flow into the gas. And also draw a PV diagram. Let's start with a PV diagram. So, first thing, reading this problem, there's multiple things going on. This is not a single process. This is a multi-step process. It says an ideal monatomic gas is compressed at constant pressure. So I'll say step A is so step A to or from point A to point B is isobaric. Heat is then added to increase the pressure at constant volume until the temperature reaches its original value. So what this means is when we go after we reach point B, we're going to go to point C, and we're going to add heat until the system reaches its original value. At this point, we're going to assume that the volume is constant. So this will be isochoric. So basically, we have a piston. So originally, we're at 12 liters. We're going to compress it at 3 liters, but we're going to keep it at 2.5 atmospheres. So we're going to let the heat leave or do something. We're going to do something to keep it at the same constant pressure. And then we're going to heat it up until it reaches the original temperature. So, I draw a PV diagram, so pressure versus volume. So we're at some 12 liters of volume, point A, and we're going to keeping the pressure constant. So the pressure is 2.5 atmospheres. We're going to decrease the volume until we reach 3 liters. After that, we're going to add heat to increase the pressure at constant rate. So the pressure is going, so this will be point B, going to increase the pressure to some point at constant rate. That gives us the point C. So calculate the total work done by the gas and the total heat flow into the gas. So when we're going from A to B, what happens to temperature? So we're decreasing volume, but keeping pressure constant. The volume is decreasing. What must be happening at temperature? But the pressure is staying the same. So in order to keep the same pressure, temperature decrease. There's a nice trick to this. And let's see if I can explain it. So when dealing with a process, we don't have to exactly look at the complete picture or the individual parts of a process. All we really need to know is we can solve this two different ways. We can assume that this B step is omitted. We can go directly to C. We don't have to, but let's let's um let's see what all we can do. So we know that this part is isobaric and this part is isochoric. So looking at your fancy table of equations, what's all we're trying to do is calculate work and heat. So from what is the work from A to B? First, so it would be isobaric. So pressure change the change in volume. So the pressure is 2.5 atmospheres. And the volume difference, so 3 liters final, that's final, minus initial, that'd be 3 minus 12 liters. Um, and we get negative 5/18 as an atmosphere times a liter, which is negative 0.27, where the 7 is carried, atmosphere liters. Did I give you the conversion factor for atmosphere liters? Yes, I do. How do you convert this into joules? Look at your notes at the bottom. It tells you a conversion factor. 101.3 joules. So if I have the conversion factor, I want joules. So I want joules in the numerator. So that's 101.3 joules per 1 atmosphere liter. I multiply this by negative 0.27 carried atmosphere liters. Then atmospheres cancel out with atmospheres, liters cancel out with liters, leaving us with just joules. So basically, you just multiply negative 5/18 times 101.3. And we get negative 28.138 carried joules, which seems like a really low value. It is. What is 2.5 times this? I divided. 2.5. So 3 minus 12 is negative 9. Negative 9 times 2.5. That should be negative 22.5. Negative 22.5. Negative 22.5. Sorry about that. So 101.3 times negative 22.5. That gets you a more realistic value. There we go. Negative 2,279.25 joules. That seems more realistic. Again, when you're dealing with heat, you should expect large numbers. All right. What about the work from B to C? 0. So isochoric tells us the work is 0. Yes. You're not changing anything. So question is, what is the work from A to C? Exactly. So we add these two together, and we get that the total work is negative 2,279.25 joules. That answers one part of the problem. Simple enough. Now let's do the same thing for heat. So what is the heat from A to B? So heat is equal to, is it negative work? So heat is equal to NCP delta T. We don't know the moles. We don't know the delta T. Let's look at from B to C. So isochoric, we get NCV delta T. All right. Uh, let's look at this. What is changing between point A and point C? What is staying the same? Pressure at A is 2.5. The pressure at C has increased. The difference between A and C is A is at 12, C is at 3. What does the problem say stays the same? So it says that we reduce the pressure, we reduce the volume, and thus the temperature decreases. But it says we then heat it up until the temperature reaches its original value. So the temperature at A and C is the same. Or in more precise language, isothermal. So what is, for an isothermal system, we know that the change in internal energy must be 0. And we know that for isothermal, the heat is equal to the work. Is it just work or is it negative work? So that means that the heat added to the system must be negative 2,279.25 joules when going from A to C. It doesn't specify a initial temperature. So instead of doing this, I should just let you watch the video. I was trying to explain it better than him, but he gives such a good explanation. Which is what we did. This was the part that I didn't have memorized. Was the alternative way. I was just showing you one. The purpose of this problem was I wanted to show you that you can take multiple paths to go from one state to another, but in the end, all you really care about is your initial and your final position, which means you could treat this as an isothermal system. Okay, that was it. I didn't remember that. So I didn't know if this would work. Apparently, you could just, if it doesn't give you a temperature, you can just make up a temperature and then calculate throughout it. So if the temperature is 1,000, what would be the temperature at 3 liters? So remember that volume divided by temperature is constant, right? Looking at your fancy table. So volume divided by temperature is constant. So the initial volume divided by the initial temperature has to be equal to the final volume divided by the final temperature. So you can do some quick math and solve for the final temperature. That's 250, right? There's a good, even better. I did algebra. So if your volume decreased by a fourth, that means your temperature would decrease by a fourth. So they're linear. If one increases by double, the other one has to double. So where does this equation come from? So it's work times CP divided by R. I didn't have this equation for you guys, so I never taught this, which is unneeded. If you want to come through here and finish watching it for this alternative, I don't get that advanced in this class. This is already too advanced. I want to drop this process in a future class and just talk about gas laws and heat equations. So, your number 4 on your homework. It says the gas is compressed quick enough that heat does not have time to enter or leave the system. So, what type of process is that? Adiabatic. Um, so, you would just have to go through your equations and solve for it. I will say this to work through some examples on this. So, using the ideal gas law, pressure times volume is equal to nRT. Note that it depends on your R value depends on what units you're using. In physics class, I tend to keep to Pascal and cubic meters. But atmosphere and liters is very useful. Do I give you the values of R for anything other than that? No, I just give it the mole and Kelvin, which means you'll need to solve for it in the correct. So let's suppose that your pressure is 1 atmosphere, which is equal to 101,325 Pascal. You have 5 moles of a monatomic gas. At a temperature of 250 Kelvin. What volume is the gas at? What is the volume? What is the volume of the gas? You can use this equation for an ideal gas, and a monatomic gas is ideal. Or we'll assume all the gases are ideal. Thus, we can do PV equals nRT and solve for volume. Volume is thus nRT divided by P. So our number of moles is 5 moles. Our R value is 8.3145 joules per mole Kelvin. Our temperature is 250 Kelvin. And we're going to divide this by pressure of 1,001,325 Pascal. So mole cancels out with mole. Kelvin cancels out with Kelvin. A joule is equal to a kilogram times a meter squared per second squared. And a Pascal is equal to newtons per, what was it? So force, or pressure, is equal to force divided by area. So an area is a meter squared. That's a newton. A newton is a kilogram times meters per second squared divided by a meter squared. So meters and one of the squares will remove, so it's equal to that. And so a joule, kilogram, is equal to second squared over meters. So a joule divided by a Pascal would thus equal, kilograms cancel out. This 1 meter and this meter cancels out. The second squared and the second squared cancel out. No. This square and this divide by meter makes this into a cube. So this is equal to meters cubed. Because we're taking a meter and we're dividing it by, we're taking a meter squared and we're dividing it by a divide by a meter, which flips it around. So that would be meter squared divided by the fraction 1 over a meter. It's the same thing as multiplying by meter over 1, which makes it meter cubed. So we get volume. So this becomes meter cubed. And thus this would have a volume of 0.102572 meters cubed. If you're curious, a liter to cubic meter. 1 liter is equal to 0.001 cubic meters. Or 1,000 liters is equal to 1 cubic meter. So this is about 100 liters. Very large amount of gas. How much of the homework have you finished? I'd like it by tomorrow. If you have any issues, send me an email or something. And I'll reply, because I think I've covered everything on the processes. Trying to see if there's anything tricky. Most of it is literally just look up the table. You don't have to memorize the table. You'll have it on the test. There's, to be honest, this entire section is, I don't like this process, except for there's only one example in which I find this useful. We'll see if I can find it. Syringe RC car. See if I can get a good picture of it. So this is an example of where this would become useful. You don't have monatomic gases. Atmosphere is mostly a combination of two gases, nitrogen and oxygen. They're diatomic. That's alright, you just look up the modified equations for CV and CP. Basically, it's your, you would just, so far, monatomic CV, I think, is 3 over 2 R. You'd have to look at your paper. And CP is 5 over 2 R for monatomic. You would just have to look out at, for diatomic, the degrees of freedom. Basically, how these numbers come about is if we look at a single atom, in what ways can it vibrate and move around? It can vibrate up and down, it can vibrate left and right, and it can vibrate forward and backward. That's 3 dimensions of space. That's the reason why you get 3 over 2. That's where the 3 comes in. Let's look at diatomic. Well, we have the same ways. It can move up and down. It can move right to left. It can move forward and backward in space. But it can do something else. It can vibrate toward itself. So it can oscillate toward itself. And rotations and other stuff. Basically, what this means is the kinetic energy can be in other forms. Other directions. I'm probably misexplaining this wrong. I just know that when you that this degree of freedom in what direction it can move adds as a source where energy can go and be stolen from its motion. So we can make this thing vibrate crazy, crazy fast without moving. It would have a ton of energy though if it's vibrating up and down. If we just have a single atom, if it's not moving in space, there's nowhere energy can go. But we can make this stay in one spot while bouncing up and down, and that will get it a lot of energy. Um, but he goes in and calculates the theoretical distance this can go. He basically has a pulley system. We did in this class. I really need to go through the pulleys, but really, we're already severely far behind. I'm not going to be able to cover all the units. You keep, yeah. um, uh, but basically, he creates. So we have some work. He has the end of this hot glued. He pulls it back. Actually, what he does is he winds the string. The string slowly pulls it back. So he's adding some energy to the gas inside the syringe. When he releases it on the ground, he's able to extract some useful work from that stored energy. And ignoring some of the friction, you can components and some of the heat. This is definitely not adiabatic because it's moving too slow. Adiabatic systems, the true ones that we can approximate, is where it's compressed so quickly that heat is unable to escape or enter the system. This guy, Tom Satin, he's also built airplanes that run off of compressed air. And his latest video, or I can't say his latest one, but the one he released like this month was phenomenal. He comes up with this is the most beautiful thing I can think of in science. He created a very, very simple piston, but that's the beauty of it. It's so simple, it's amazing no one thought of it. It works so well. It's basically a pneumatic. See if I can look it up. Because he had like a lot of huge people talking about it. Um, let's see if I can. I want to find his animation. So it takes a 2 liter bottle and he pressurizes it with air. So, so the 2 liter bottle is screwed in right here and is under high pressure. So this white area is high pressure. It's pushing this ball against this rubber O-ring, sealing it so none of the gas can escape. So as soon as this pin pushes it, air's gonna rush in here. And this is sealed right here. This tube is sealed, so none of the air can escape. Now, this thing, the end of this is basically a spinning propeller. So it's going to have some angular momentum. Things that, unless you add a force to it, or torque, things that are spinning want to stay spinning. And so this diagram is going to want to keep moving back and forth because it's connected to a spinning propeller. So the momentum, the angular momentum of the propeller is going to keep this moving back and forth. But there's frictional forces, so eventually the propeller will come to a stop. But this is going to introduce some more torque to it. It's going to push this diaphragm back, which pushes on this gearbox, and the gearbox basically converts linear motion into angular motion, rotational motion. But that's some very advanced setups that you can analyze. The RC car is very simple to analyze. Tomorrow, I'm going to go way more into gas lab or gas still, and then we're going to do some implosions this week.